Welcome back. We are covering section 3-9. This is derivatives of exponentials and logs. So, one of the great things that I love about this book is how they write out these formulas, because from here on forth, they're really emphasizing that everything's a chain rule. Okay, in a lot of the common calculus books, they'll give you this equation. They'll say the derivative of e to the x is e to the x. And that is actually technically correct. But that's not the whole picture, because this is a chain rule still. The outside function, as we've been talking, is this e function, and the inside function is this x function. So the derivative of e to the x is e to the x, but it's times the derivative of the inside function, which is x, which in this case is 1. Okay, so here's how your book describes it, which I think is a better definition. The derivative of e to some function. So this up here, this is your inside function, and it can be anything. It can be a whole mess of stuff, but the idea is e to a big mess, whatever that is, okay? And the formula for the derivative is e to that big mess, just as it's written, rewrite it, but then multiply it by the derivative of that exponent. And this is a really more thorough definition of how you get the derivative of e to the x. Okay, so let's do an example. We're going to find the derivative of e to the sine of x squared. Okay, so using our formula, we first need to identify the outside function. Well, that's the e, okay, and the inside function is sine of x squared. So my derivative is going to be e to the sine of x squared, same, times the derivative of that whole exponent, sine of x squared. Again, I would recommend you writing this derivative notation, because you don't want to get lost in the fact that, hey, now when I take the derivative of this, it's a chain rule again. Outside function is sine, and inside function is x squared. So we're going to rewrite this. The e to the sine x squared comes along for the ride, and let's talk about the derivative. The derivative of the outside function, which is the sine, is cosine, evaluated at the inside function, which is x squared, times the derivative of the inside function, which is x squared. All right, so one last step. Cosine of x squared times the derivative of x squared is 2x. So again, I like to put that 2x in the front just so we don't get that mixed in with the angle of the cosine. So we put it like this. All right. That is how you use this formula for an exponential function. Now these exponentials can be, again, paired. This feels very much like the trig section. They can be paired into a product rule, into a quotient rule, all that stuff. So for example, e to the 2x, cosine x. This, on the onset, although this is a chain rule, the big picture is that these guys are being multiplied. This is a product rule, and we'll have a chain rule within it, but initially I'm going to write out the product rule. So dy dx is the derivative of the first term times the second term, plus the derivative of the second term, or of the second term, times the first term. Okay, now let's take a look at these two little derivative parts and do those. The derivative of e to the x, e to the 2x, everything's a chain rule. Outside function is e, inside function is 2x. So the derivative of the outside function is e, evaluated at the inside function, times the derivative of the inside function, times the cosine of x. Okay, the derivative of cosine is negative sine. times the derivative of the inside function, which is 1. And then e to the 2x comes along for the ride. So our final little cleanup here, the derivative of 2x is 2. And then minus sine x e to the 2x. Now, I think this is just good to see. I wouldn't mark you off if you left it here, but I always like people to notice when things factor out because that often leads to simplification. It does not in this case, but I just want to show it to you so that you start to notice it. Both of these terms, there's only 2 terms. They're separated by a subtraction sign. They both have an e to the 2x. So I can factor that out front, and that leaves me with 2 cosine x minus sine x. And the reason it's good to see that is sometimes this inside will either a simplify or, like if we're in trig land, it could be a Pythagorean identity or something like that that would simplify down. So it's good to just take a look at that if you can factor anything out. And I think you'll find that the answers in the back of the book look like this, or I mean, not in the back of the book, you're online, but you know what I'm saying. The answer format looks like that. Okay, so those are some examples of e to the x. You can now try, if you want to pause the video, try example 3.75, and then we'll come back and talk about some more stuff. Okay, hopefully you actually stopped that and did it. That's how you interact with this and get the most out of it. The derivative of a logarithm. We're going to start actually with a natural log. The natural log and the log have 2 slightly different formulas. They are related. One comes from the other. But say we want to take the natural log or the derivative of natural log of g of x. Now, again, what this g of x notation is, it's just the natural log of a bunch of stuff. Okay? So and this could just be an x in here, or it could be a big fat polynomial. It could be a rational function. It could be all sorts of stuff. Okay, but the way you take the derivative is you pull out that stuff and you take 1 over all of it, no matter how bad it looks. It's just 1 over all that stuff that you're logging, and then you multiply by the derivative of that stuff. Again, this is the chain rule. So the derivative of the outside function is 1 over, that's the formula if you will, and then times the derivative of the inside function, g prime of x. Okay, so let's take a look at an example. We've got, let's call it something, f of x, natural log of x squared plus 3x minus 4, and I want to find the derivative. So my outside function is natural log. My inside function is this polynomial. So when I'm taking the derivative, I go, okay, my outside function is natural log. So that leads me to this formula. And I'm like, okay, the way I take the derivative of log is I put 1 over the stuff. All right, so this is going to be 1 over all the stuff. And then I'm going to multiply by the derivative of all that stuff. So the natural log goes away when you do the derivative. Okay, and the derivative of the inside function there is going to be 2x plus 3. And if you choose, that can go on top. A lot of times it's worth trying to factor things and see if they cancel. In this case they won't, but you could see that this factors as x plus 4 and x minus 1. And that's worth a check because sometimes some things will cancel. Okay, and that's your answer. All right. One more example of those. Yeah, I'll do one more example and then we'll kind of speed up a little bit. There's some examples in the book if you need more. Okay, so this one. Again, chain rule. Outside function is natural log, so I know that I'm using this formula up here. The inside function is all of this. So my derivative is going to be 1 over all of that inside function times the derivative of that inside function. Okay. Now we're going to take the derivative of this. What is it? It's a quotient rule. Okay, so this is quotient. So that's what I'm going to write out. In the meantime, I'm going to simplify this fraction. The way you simplify fraction on top of a fraction is you take the denominator and you flip it over. So this becomes 2x plus 1 over the x squared sine x. And now I'm going to do the derivative of this quotient. So low d high minus high d low square the denominator, away we go. Okay, so this 2x plus 1 hangs out over x squared sine x. And let's do these little derivatives here. This one, okay, this is a monster of a problem, okay, but it's why I wanted to step into it a little. Just need you to see it. This right here is a product rule, okay? So, derivative of the first term times the second term plus the derivative of the first term times the second term. Okay, and then the derivative of this right here is 2. This is really an exercise in being careful with writing down the details. If you drop off a part of this, don't recopy it. Each time you're going to lose something. So you just go slow and steady and make sure you recopy. You know I make a lot of mistakes and it happens, but just try your best to keep track of everything. Okay, so I've got a 2x plus 1 here. Now, the derivative of x squared is 2x, and then I've got a sine x, and the derivative of sine x is cosine x times x squared minus x squared sine x and a 2. I'll switch that order in a second. Okay, so let's see, what do we have here? I'm looking for common terms in the top. I see that there's an x term in each. I don't know that that'll be helpful, but let's just multiply this out. I'm going to take this guy and distribute it in to both of these terms. Times 2x times sine x. And then I'm going to just switch the order of these. I like to put my polynomials first, my trig functions last, and then also just pull the 2 in front of here. 2x squared sine x over 2x plus 1. Now what I'm really interested in is, can I factor a 2x plus 1 out of everything on the top, because that would create a canceling situation. And that is not true, okay? However, I see that I just widened my gaze a little and see that I have a 2x plus 1 right here that will cancel with one of these down here. So that's good news. But what I do see on the top of this big fat fraction is I see that this, let's see, not the 2. I see that this term has an x. Erase my parenthesis. Okay. And I see that this term has an x and this term has an x. These last two have more than an x. They have 2, but at least they have 1. So let's factor that out of the top. So this now out front is 1 over x squared sine x, because the 2x plus 1 canceled. And I'm pulling an x out front, and that leaves me with still this 2x plus 1, a 2, and a sine x. And then my second term right here, I have 1x left and a cosine. And this term, I have a minus 2x sine x. 2x plus 1. Okay. And then this x can cancel with one of those down there. And I think that's all we can do. So my final answer, and you can shove all these together if you want. I'm going to just take these and put them into the denominator. Since this is a 1, that doesn't change anything. So I've got 2 times 2x plus 1 times sine x plus x cosine x minus 2x sine x, and put that all over my x, 2x plus 1, and my sine x. Okay, and that's my answer. What I would suggest that you do on this problem, this is a reasonable problem. Like, this is what we want you to get really good at. So although it's long and it's complicated, if you can do this, you really can do anything. So I would stop the video and I would try, I would come up here and I would write this down and see if you can do that. Okay. And as always, if there's a typo in here, let me know, but I'm trying to be careful. So try that on your own, check your work, see if you get where you think you should. All right, another formula for two, let me do 2 at once here. The derivative of a regular log function. So this is a log of any other base besides e. That is going to be, it's similar. It's 1 over the stuff, whatever you're logging, but also down here is a natural log of b. B is your base, whatever that is, times the derivative of the inside function. Now, why is this different? It's actually not different from your log. Your log formula, your natural log formula was natural log of g to the x, of g of x, equals 1 over g of x, g prime of x. It's actually, this is actually this, but the issue is, let's look at this derivative using this formula. I get 1 over the stuff times the natural log of the base. The base on this right here is e times the derivative of the function, and this right here equals 1. So that then gives me this formula. So really, if you're, I mean, again, I don't need you to memorize all these formulas, but as you go on in math, sometimes it is advantageous to memorize. If you do, this is the only one you really need to memorize, and the natural log just comes out in the wash because you're going to take the natural log of e. So I just wanted to point that out. So this is one formula for the second part of this section. And then the other one I want you to know is how to take the derivative of an exponential. So remember, these are like 3 to the 5x or something like that. That's an exponential function. So this b is a number, and then this is a bunch of stuff. And the way we take the derivative of that is we take the function, the exponential as it is, very much like the e function, and then multiply by the derivative of the stuff, and then multiply by the natural log of the base. And again, this is the more general formula of that e formula. It's just that natural log of e is 1. So you can kind of similarly compare those two. So this top guy, let me erase all these markings here. This top guy and this bottom guy are the main formulas, and the other two come out of those. I also want to note, for the record, I think there's a typo in your book. They put, for this right here, I think it says g double prime, at least it does in my copy, and that is not right. Okay, it's just the first derivative. So if that's in your book, don't be misled by that. Alrighty, let's do one of these. We'll do a simple one of both of these. Log 2 of 3x plus 1. So this is a log base, so dy dx is going to be 1 over the stuff times the natural log of the base times the derivative of the stuff. So that this derivative right here is just 3. So my answer is going to be 3 over 3x plus 1 natural log of 2. Okay, that's your answer. All right, so that's an example of the log, and then an example, just a simple example of the exponential, y equals 3 to the x squared. So dy dx is going to be the exponential times the derivative of the stuff times the natural log of the base, which is 3 in our case. So this is the only part I need to do further. So I get 3 to the x squared times 2x times the natural log of 3. And that's it. That's your answer. Reduce if you can. So that's how you use those. And then I can couple any of these type of things in with a product or quotient. I won't go through all the possible combinations of that, but they work just like that one long example I did. All right, and the last thing I want you to see in this set is how to do a technique called logarithmic differentiation. And this is, that's not how you spell it, T-I-O-N. This is a really powerful tool, and actually if you could grab this section, you could go back and do most of the previous sections a lot easier. I play around with introducing this first every time I teach it, but there's some issues with doing it that way. So this will really make your life better if you can follow me on this. If I have a function like, let's go 2x to the fourth plus 1 to the tangent x. Okay, and I want you to find dy dx. One way, this problem, actually you have to use logarithmic differentiation because you have a bunch of stuff as a base and a bunch of stuff as an exponent. Whereas before, like in this previous problem, we had a number as a base. So this doesn't actually follow any rules that we have so far, but I'm going to show you how this technique applies to some simpler problems after this. The idea of logarithmic differentiation is before you take the derivative, okay, before you take the derivative, you take the log of both sides. So log of y, and you take the log, and it can be natural log or regular log, doesn't matter what base you choose, okay, up to the tangent x. And then you use the log rules from pre-calculus to reorganize the problem. Okay, so for example, in this case, I have the log of an exponent. And so we had that rule that said, hey, you can bring the exponent down in front of a log. So this becomes tangent x ln of 2x to the fourth plus 1. And now what that does is it turns this into a product rule. Whereas before we didn't have any rule for this. This is not an exponential. It's not anything we've studied. I don't really know how to handle it. Now it's a simple product rule, and I do know how to handle that. Okay? But the trick is, because you have this over here, you have to do implicit differentiation. So you have to differentiate both sides and do it carefully. So the natural log of y, the formula for the natural log is 1 over the stuff, right, times the derivative of the stuff. Okay, so that's the derivative of the left side. Now we're going to do the product rule. Derivative of the first term times the second term plus the derivative of the second term times the first term. Okay, so let's take these derivatives. This derivative, we'll come back and deal with the left side at the end of the problem. Okay, derivative of tangent is secant squared. And then I've got my natural log coming along for the ride. And the derivative of this is a chain rule. So the outside function is natural log, and that says 1 over the stuff times the derivative of the inside function, which is 2x to the fourth plus 1. Okay, times our tangent x. So one last derivative ln of 2x to the fourth plus 1. 2x to the fourth plus 1 times, this is going to be 8x cubed, and then you got your tangent x. And that's probably about all you can do. I can throw this upstairs if you want. I like to have my natural logs in front. That's a personal preference, not critical. And I'm going to throw my tangent upstairs too, make this one fraction. All right, and that's your derivative. Okay, now here's where the left-hand side comes into play. Okay, this is not dy dx. This is the derivative of the right-hand side. The left-hand side has this. If I want to know what dy dx is, then I need to solve for dy dx. So in order to do that, to get this alone, I'm going to multiply through by y on both sides. So dy dx is going to be all of this stuff times y. Now what is y? We go up to the top to see what y is. This is going to be 2x to the fourth plus 1 to the tangent x. And this is the derivative. So there's just one extra step with logarithmic differentiation. Okay. Now, let me show you where this is a really powerful tool. Let's look at, because this may not feel easy to you. I mean, that may seem complicated, and it is. But the problem is, this is the only way we know how to do a bunch of stuff to a stuff power. That you have to use logarithmic differentiation. But let's look at one where you don't. You don't have to do that on this problem. X squared plus 3x, and then 5x cubed minus 1 cubed. Okay, so if I want you to find the derivative of this, this is just a product rule, right? Okay, the problem is that when it's a product rule, but there's a chain rule embedded in it. So it's the derivative of this first function times the second function plus the derivative of the second function times the first function. Okay, and then this derivative is a chain rule. Now, I'm not going to walk this all the way through, okay, but I hope you can see that this is a little bit of a process here, okay? However, if you want, you can take the natural log of both sides. Again, before you take the derivative. Okay, and if you remember the rules, if you have the natural log of two things multiplied, you can split that apart into the sum, the natural log of the sum of the natural log of each term. Okay, so that breaks up your multiplication. Not only that, but this power comes down in front. So I actually get squared plus 3x plus 3 natural log of 5x cubed minus 1. So look at what we've done. We've eliminated the product rule. Not only did we eliminate the product rule, but we also eliminated the chain rule with that power coming down. So now I'm just going to take the derivative of each of these terms, okay, which is a lot simpler. So let's go. Natural log of y, derivative of that is 1 over y times the derivative of y. This is a chain rule, but it's a simple chain rule. I've got 1 over the stuff times the derivative of the stuff. Okay, and then similarly, this 3 just comes along for the ride, and the derivative of this natural log is 1 over the stuff times the derivative of the stuff. Okay, so I get 1 over x squared plus 3x times 2x plus 3 plus 3 over this fraction times 15x squared, and that's it. Okay, so I think this is pretty nice. If you can do this on any problem you want. What's 3 times 15 is 45 over this stuff. Whoa, cubed minus 1. Okay, and then all you have to do at the end is multiply by y. So dy dx is this stuff plus 3x plus 45 over 5x cubed minus 1 times the y value. And we go up to the original equation, which was right here. Here's what y was. X squared 3x times 5x cubed minus 1 cubed. And that's it. That's your answer. Okay, so that's logarithmic differentiation. It also can get rid of a quotient rule. Maybe I'll just do this one really quick. It's a very simple one. This guy, when you take the natural log of y, the natural log of a quotient goes into subtraction. So this becomes the natural log of x plus 3 minus the natural log of 2x minus 7. So this becomes 1 over x plus 3 times the derivative of the inside function, which is 1, okay, minus 1 over 2x minus 7 times the derivative of the inside function, which is 2. And this is 1 over y dy dx, and then you multiply through by y. So it's this series times your y value. And if you add, so some of you might be saying, hey, that doesn't look like the quotient rule. No, it doesn't. But if you add these two fractions, you get a common denominator, and add this up and then multiply by this, then it'll look like the quotient rule. So that you have to manipulate it a little bit algebraically, but it is the same thing. And a lot of people think that this is easier. So if you want to use this going forward, feel free. And I'll see you for the started chapter.